Ladies and gentlemen, my name is Flavio Ortigão. I am the founder and the Chief Technology Officer of both Recupera and Relab. And I want to talk to you today about Syngas. So bear with me, I will share my screen. So hold on for a second. I have a part. This is a PDF. I have to find that. Okay. So let's start by defining what syngas is. And syngas is a gas mixture composed essentially of hydrogen and carbon monoxide. Pay attention, carbon monoxide, not carbon dioxide. There is a huge difference between carbon monoxide and carbon dioxide. Carbon monoxide is not fully oxidized, is a gas with chemical characteristics. It has energy. Carbon dioxide is fully oxidized. It has burned all its energy and you cannot do any chemistry with it, basically. So carbon monoxide is what we want. Carbon monoxide and hydrogen are common commodities for the chemical industry today. They are using for driving chemical process. By the way, syngas is a commodity in the industry today. So the gas may contain carbon dioxide and methane and other contaminants, depending on how it was done and from which material, carbonaceous material, carbon-containing material, the gas is derived. You may have some contaminants that you have to purify if you want to have a more pure gas. But for burning the gas, purification is not necessary. You can burn, and syngas will always burn, and that's why it is considered a fuel gas. But as I will explain later, we are not interested in fuel. We are interested in syngas as chemicals. Then let's talk about the history. Some people will say, well, syngas or gasification technology is something new. And I always say, well, not really, not quite new. 200 years. We are now in 2023, and syngas was invented or introduced into the market 1823 in England under the name street gas. And it was produced by the gasification of anthracite coal, and anthracite coal, of course, is mineral coal, and it was for the purpose of street illuminations, good for the whales, because before that, people use whale's oil. So in substitution for whale oil, it was an advancing. And also in the history of this 200 years history, the largest producer of syngas occurred during the war. German producing 450,000 tons of syngas in 1944 for their military effort. And they use mineral coal, which they have a lot, and they gasify and produce diesel. It's also under the name syn diesel, but you can produce a diesel out of syngas. It's one of the possibilities. After the war, but fossil oil become available and become also very cheap. And that is the reason most of the countries, they gave up the utilization of syngas for transportation. forgetting that syngas was very flexible because you could use coal, you could use wood. The process was called dry distillation. They did not call gasification, they called dry distillation of wood, but it is gasification. The process continued though in South Africa after the war because of the boycott they had. They could not have access to other fuels. So South Africa continued to producing syngas out of coal, of their coal reserve. And they are today the largest producer of syngas. All their oil and chemicals produced in South Africa are derived from syngas. So it is a very well established technology. Uh, what we have done is, of course, we took up these technologies of producing syngas, no, and revisited them. And specifically, what we do is design here is CNCH, that stands for hydrocarbons. Plastics are hydrocarbon. So but also could be coal, could be biomass, any carbon containing, but we chosen to work with plastics for a reason that is much simpler to gasify plastics than anything. The technology we use for the gasification is steam cracking. So steam cracking is also not new. This is a process that is being used by the oil industry. That's how oil is cracked to naphtha. They use a steam cracker, which is a form of gasification. So you react the carbon, the hydrocarbon or the plastics with the steam, and you obtain CO and hydrogen in this proportion. Oh, CO and hydrogen. Normally, you want to have for each CO, you want to have 2 hydrogen. That is a very good proportion for doing chemistry. But this is basically very well known. So we are not doing anything new. What is new with our technology, both Recupera and Relab, is that we do this process at low temperature. Normally, this process is carried out at 4,500 high temperature. And this is, of course, plasma, but you produce a very good quality gas, but it's very expensive. It's very expensive, and most it's not viable, economically viable. Most processes I know are not economically viable. This is the reason why gasification is not widely adopted. So we have, around for many years ago, reduced the temperature, and make the process autothermal. So the process has its own energy because plastics have enough energy to drive the process. So by reducing the temperature, we use the chemical energy which is available in plastics for driving the process. There is no external demand or input of energy in the process we run. That is why it becomes economically feasible. So when you have a carbonaceous, carbon-containing material, you can gasify, and when you gasify, you will obtain a gas, essentially hydrogen and carbon monoxide, but also can have other contaminants depending on how you control your process and the start material and the nature of the oxidant, because when you use air as the oxidant, you are injecting nitrogen, of course, and then you will have what you inject in the process is going to come out. So it depends of what you are using for oxidant. But then you have a gas, and this gas you have 2 options. If you want to use the gas as a fuel for combustion, you don't need to worry about purification. You may have environmental concerns, but not chemistry. It works even a very dirty gas will combust, will catch fire. So you will get power and heat of a very lousy dirty gas. Now, if you choose on the other way to go for production of chemicals, then you need to have a high quality, because low quality gas will poison the catalysts, because the next process, what we call the downstream process, they require very expensive catalysts, and you don't want to destroy them because your process become then uneconomical. Now, if you do that the right way, you will end up with a clean gas, and that clean gas can be used directly, syngas, for the chemistry. What chemistry? Everything. That's the nice about syngas, its flexibility. You can do the whole chemistry out of syngas. There are the low-hanging fruit. You can just separate the gas, and then you have on one line carbon monoxide that the industry use for carbonylation. So the chemical industry uses carbon monoxide for all the carbonylations, carbon addition reactions. So you use the CO. And hydrogen, I don't even need to speak, because by now everybody knows how important hydrogen may be. And this is a route of producing hydrogen. That is why we say we consider plastics as carriers of hydrogen, solid organic carrier, because it's very simple to take the hydrogen out. And the hydrogen, of course, you can produce ammonia. From ammonia, you can produce urea, and then you have fertilizers here. But syngas can be used directly for production of methanol. Now, methanol is one of those, is a C1 compound, and it's one of the entry compounds in the chemical synthesis. Out of methanol, you can do everything. So you can produce the whole chemistry out of methanol, including, here's the name, olefins, new plastics. And most of plastics are olefin, polyolefins, and we can convert plastics to plastics now by converting syngas to methanol and methanol to olefin. Those reactions, they are established standard operation procedures in the chemical industry. So there is nothing new there. All the technology, all the equipment, all the process are very well known. So this is drop in. You can have a compound that you can drop into the chemical industry for producing those syntheses. That is why we chosen to use syngas as a route for the conversion of waste plastics, because we want to convert plastics to plastics. And this is, of course, a circular economy. That is what I'm telling you. There is here a process, a well-known process, 200 years old, that can be used, can be revisited to produce circular chemistry. I hope with that I was able to explain to you the importance of syngas. I thank you so much for listening, and well, have a good day. Bye-bye.